Hello, everybody. My name is Pasquale Steduto. I've been working for FAO in the last few years, first as a chief of the water service, then as a deputy of the Land and Water Division. And then I moved to the Near East and North Africa region, where I was a regional program leader for FAO and manager of the water scarcity initiative. Then last year I retired. Presently, I'm a senior water advisor. In my presentation today, I will address the terminology that you will be using during the training on real water saving as proposed by Future Water, and that you generally encounter when you deal with water resource management. The various terms that you may encounter are water use, water consumption, return flow, water saving, water efficiency, and water productivity. And let's start with the water use. I would maintain for a little while the parallelism between the use of money, the use of energy, and the use of water. They all have a multiple use. In the case of money, you can allocate the resources to different goods and services, like to receive medical care or food or for a vacation, anything that you consider is appropriate to use the money for. In the case of energy, also, you have a multiple use of energy. It can be used for illumination, for transportation, for pumping, etc. In the case of water use, you also have an allocation. You can go for for instance, for the production of electricity, or for industry, or for urban sector, for navigation, for environment, but also for irrigation, which will be a major, let's say, domain in which you will be working with. In the case of water use, we refer to the amount of water that is applied to a specific purpose. Like we were saying, can be irrigation, power station, industrial processes, etc. And you have to consider that to be applied, water is removed, diverted from its source. So another term you encounter is withdrawal. In terms of water consumption, we may look at the same parallelism between money, energy, and water. And here we needed to recognize that while for the case of money, um, once they are used, they are also spent or consumed. Similarly, for energy, once it's used, it's also consumed. It is gone. In the case of water, there is no strict correlation between the use and the consumed water. And that's why now we need a clear distinction to make. The water consumption, in fact, refers to the portion of water use that escapes the system by changing its phase from liquid to vapor after having exercised its specific purpose. So we consider that water is consumed when escaping the system. It goes under the form of evaporation and or transpiration, which are the change of phase from liquid to vapor. And this is the major fraction of water use that is also consumed. We have to recognize also that different water uses have a significantly different evapotranspiration. And here now we will look in fact to three particular cases and what are the expected difference in evapotranspiration. We'll consider the case of hydroelectric power generation, household, and irrigation. In the case of hydroelectric power, essentially what we have is that water goes from the dam through the turbines and to the river downstream. So the turbine converts the kinetic energy of the falling water into mechanical energy. Then a generator converts the mechanical energy from the turbine into electric energy. In this case, what is the water consumed? Essentially, is the water that is evaporated from the dam. And generally, it can be of the order of 10%, but this is very variable, depends how big is the dam, how much surface from the dam is exposed to uh, the solar radiation, to the atmosphere. In the case of household water, essentially, what we have is that water goes from the house main inlet pipe to the kitchen, to the washing machine, dishwasher, bathroom, etc., and then exit home through the drainage system. So, what we expect is that the water consumed as evaporation is not high at all. It may be of the order of 5%. One thing for sure, though, is that the quality of water is altered after being used. In the case, for instance, of the hydroelectric power generation, we have seen that the quality is not expected to change at all. But in this case, it changed significantly. In the case of irrigation, we have that the water essentially get diverted from its source, can be groundwater, surface water, etc., through the distribution system, can be either collective or individual. It goes to the field irrigation system and ultimately applied to the soil. Most of the water stored into the soil root zone will be used by the crop evapotranspiration. Furthermore, depending on the level of uniformity and efficiency of application, there will be fraction that will run off and or percolate out of the field. In this case, actually, the water consumed is quite high. It can be of the order of 50 up to 90%, depending on the efficiency of the systems. And that is why agriculture is considered the largest water users and consumer. Also, in this case, though, we need to recognize that the quality of water is altered after being used. Let's talk now about return flow. In the previous case of irrigation, we have observed that there are two fractions, runoff and percolation, that quantitatively are not consumed. They are still in the system in liquid phase, although they have changed their original quality. These two fractions are also referred as return flow. Essentially, with the return flow, we indicate that the fraction of water that after being applied to a specific use, they go back in some form to the system under liquid phase. You can, for instance, take back the example of the electric power plant where the water, after being used to generate the electricity, it goes back to the river downstream, and that is the return flow for the case of power generation use. Similarly, in the case of household, after being used into the house, it returns to the system, although with different quality and so on. So we consider those fractions that still remain in liquid phase that return to the system after being applied for a specific purpose, we define them as return flow overall. But let's use now a structured way of framing the different fractions of water use, particularly referring, of course, to irrigation. We will use the framework that represent a sort of water accounting, and you will be using in the real water saving training. Here you have that water used can be distinguished into two forms. we have said the consumpting water use, so consumption, is the one that change phase. It goes into evapotranspiration. And the quota that instead returns to the system, either runoff, percolation, and in form that is called return flow. We can also further subdividing the consumption fraction in beneficial and non-beneficial consumption. For instance, the beneficial are typically the one that belong to a crop. The transpiration of a crop, through its transpiration, it generated the biomass and then the yield. This is what we are looking for, and then we refer as beneficial. But there are other forms of beneficial use. But the non-beneficial, for instance, are the one that are through the form of evaporation of bare soil or free water surface evaporation, like in the case of the dam. And also, of course, the transpiration part of those weeds that are in your crops. But there is also a subdivision for the return flows where we have a quota that can be recoverable and a quota that might not be recoverable. So what is recoverable? Is recoverable the one that is used maybe downstream by other user or goes to recharge an accessible groundwater and so on. So when it's recoverable means you can reuse it. When it's not recoverable, really it goes in systems where they are not accessible anymore. For instance, imagine you are toward the coastal area, and your runoff goes into this into the sea. In that case, you cannot recover anymore that quota, so is lost in a way. So also this part is not accessible, so is leaving the system and is not recoverable. Similarly, it can go in deep percolation in groundwater systems that are very saline or very deep. So in this case, again, is not recoverable. So this distinction between what is recoverable and what is not recoverable is very important when we do the analysis for water saving. And in fact, it is important to recognize that when we want to save water, there are two major fractions that we can, let's say, refer to. One, if we reduce the consumption, so the evapotranspiration, either beneficial or beneficial, of course, we can optimize that consumption. But when it's consumed, if I reduce the consumption, that I can save water. Similarly, if I'm able to avoid or to reduce the non-recoverable fraction of the return flow, these two components can be considered of value for saving water. In fact, now passing into water saving, we can define that water saved is the amount of water resulting from a reduction in consumption or evapotranspiration and or in the non-recoverable fraction of the return flow, and that can be made available for alternative uses. The water saving, we use this term to refer to the technology, practice, and measure, here overall indicated as intervention, leading to the above-mentioned reduction in consumption and in non-recoverable fraction. Now, linked to water saving is another important question, is the efficiency. If we increase efficiency, like in the case of irrigation water use, are we also saving water? Well, it's a key question, and we need again to look carefully at the different fractions. So let's first see what happened to this various fraction of irrigation water when the efficiency is increased. And we'll use the same example of irrigation of before, But we define here now efficiency. Efficiency is the ratio or the fraction between the water consumed via evapotranspiration over the water amount that has been diverted for irrigation. So assume for a moment that the efficiency increased from 50 to 85%. What happened to this different fraction? Well, the diverted water is decreased. The same also the irrigation as a consequence in decrease, while the evapotranspiration has basically no change because it's the quota that you want the crop to transpire in order to generate its yield, but also at the same time, runoff is decreased, percolation is decreased, the stored water in the root zone has no change because it's linked to the evapotranspiration. So we have this decrease of liquid component in the diversion, irrigation, and return flow in runoff and percolation, like we said before. Now, what this reduction in those fractions means in terms of benefit, and also who is really benefiting? Let's put ourselves in the shoes of a farmer. From the farmer's perspective, runoff and percolation are fraction of water that can be recovered and reused to extend the irrigated area and or intensify the cropping system. Essentially, the farmers perceive this fraction as a losses. They are leaving his farm, they are leaving his system. And particularly when he is under water scarcity condition, these fraction are considered precious additional water resources. So it will tend to recover all this water and utilize for intensification or for expansion. From the irrigation district manager perspective, the reduced diversion allow to reallocate more water to other farmers downstream. So it's a more equitable and performing operation. So you also, like the farmer, has some benefit. From the water basin authorities and water resource minister perspective, instead, those reuse of runoff and percolation and the reallocation to other farmers is not providing any water saving. So who is losing is the larger scale. Who is gaining, who is benefiting more is the farmer and eventually also the irrigation district. So that's why you need to follow the water at its fraction to understand who is benefiting from increasing the efficiency of irrigation and if you are achieving real water saving. Last terms that we will present now is water productivity. Very briefly, the water productivity refers to the ratio of the benefits derived from a production system to the amount of water consumed to produce those benefits. Essentially, is the ratio of net benefit over water consumed. And in agriculture, generally, the production system are the crop, livestock, aquaculture, mixed system, integrated system, etc. And the benefit can be either biological, like biomass yield, the kilocalories and protein, but also economical, like incomes in dollar, in monetary terms, or even social if they generate more job. So generally, water productivity is dimensional. So you have a kilogram per cubic meter or dollar per cubic meter or job per cubic meter, and is not confined to the theoretical limits of the efficiency or the engineering or hydrological efficiency 0, 1, when both numerator and denominator have the same units. So increasing water productivity is one of the main response options to water scarcity. And with this, I'll stop and I thank you for your attention.